For our fourth and final video on chapter 19, we're going to introduce a new theory of bonding. It's called crystal field theory, and we use it to describe spectroscopic and magnetic properties of coordination compounds. And this chapter is kind of bringing in the basics of inorganic chemistry. You've probably heard of organic, and some of you will continue on into that next year. But this is its sister course, inorganic chemistry. This is what that's kind of all about. So these transition metal complexes, we saw in the previous video, they adopt some different geometries because their bonding is different, right? And the behavior of those bonds is different as well, which should be obvious because right at the beginning of the chapter, we talked about the fact that they form coordinate covalent bonds. And the geometries that these things adopt aren't consistent with hybridized orbitals, which we discussed last semester. Remember, like an sp3 or an sp3d2 hybrid orbital. Right? But what we see with coordination compounds isn't consistent with that. So we don't use valence bond theory, shown here as VB theory. Yep. And the fact that transition metal complexes are often colored, as we've referred to earlier, indicates that our d orbitals are at different energy levels. They're not degenerate, meaning it's not what we've said when it was oversimplified in the past, where all the d orbitals are at the same energy level, right? The color indicates that that's not the case. So to explain what's going on with coordination compounds, we use what's known as crystal field theory, or CFT. And essentially, what crystal field theory deals with is electrostatic interactions. So we're thinking about charges, okay? Specifically negative charges, looking at the electrons that are on the ligands and the electrons that are in the d orbitals on the center metal. Okay, so we've got electrons that already exist on our metal floating around in d orbitals, and then we're thinking about the electrons that are also coming in from the ligand to form the coordinate covalent bond. Okay? All electrons are negatively charged. All electrons repel one another. Okay? So what we need to think about with crystal field theory is the shape of the d orbitals. Okay? The fact that everything that's coordinate 6 is octahedral, and then the 6 ligands that come in to form an octahedral complex. So let's look at the shapes of those d orbitals. It's been a while since we've seen those. Now, if I have a metal that doesn't have any ligands and it's in the gas phase, then all of these d orbitals are equal in energy to one another. And I would expect the electrons to be equally distributed between them, right? Following Hund's rule. But when ligands come in and bond to the metal, these guys are no longer in the same energy conformation, which is what our next slide is talking about. Because two of those d orbitals, the dz squared and the dx squared minus y squared specifically, okay, the lobes of those orbitals end up pointing directly at where the ligands are trying to come in. Okay? So those two orbitals are called the E sub g orbitals, and they're higher in energy because the electrons are pointing right at the ligand. Okay, so those electrons are really close to one another. Now the 3 remaining d orbitals, the dx, y, xz, and yz, those have lobes that point between the ligands. Okay, so they'd obviously rather be nowhere near anybody, but at least they're lower in energy because they're not pointing directly at a ligand, right? Those higher energy ones, the electrons are pointing right at one another. These other ones are kind of pointed off in space, okay? And those are called the T2G orbitals. And because of the electron repulsions that I've been talking about, there's differences in potential energy. And those guys are named based on their symmetry. And you see the names over here, EG and T2G. And you see now there's an energy difference between the two, okay? If we look at this energy diagram. And that energy difference we call delta OCT, and the OCT stands for octahedral. And the difference between those two energies, which comes from crystal field theory, is called crystal field splitting. Okay? And every complex has a different value of delta OCT, that energy difference. And it depends on a couple of things, right? What kind of ligands are bound? How many ligands are bound? The charge or oxidation number on our metal. And what d orbitals am I dealing with specific? What are the valence d orbitals? The 3d, the 4d, or the 5d? Okay. And different ligands can, as I've just said, give you different values of delta OCT. And those are measured in something that's known as the spectrochemical series, which is shown on the top of this slide. The spectrochemical series, which goes from iodine on the bottom end to cyanide on the top. Okay. And we kind of cut these guys in half here, and we think about the ligands on the left, right, the lower end. Those are called weak field ligands, and those are things that give us a really small value of delta OCT. The energy levels aren't split very significantly. But the guys over here on the right-hand side, those are known as strong field ligands. They cause delta OCT to have a large value, and those energy levels are further apart from one another. And that's significant because it has an impact on where my electrons go. Even though we have a different theory here in crystal field theory, we're still following the aufbau principle from chapter 6, right? From the bottom up. Our electrons still fill the lowest energy orbitals first. But the whole challenge in chapter 19 at the end here is thinking about the crystal field splitting, delta OCT, and comparing that to the pairing energy for two electrons in an orbital, because that can change the properties of a metal. And that's best seen by looking at this diagram, right? And you see here two iron complexes where the electrons fill in differently. Okay. Now, my iron 2+ has 6 d electrons. Okay. And you could figure that out from the electron configuration. Write out the electron configuration for iron, neutral, it's iron 2+, so you lose the s electrons. You have 6 d electrons. If it didn't have any ligands, right? These guys are all the same in energy. So I fill them in 1, 2, 3, 4, 5, according to Hund's rule, right? Fill all the boxes before you double them up. The 6th one is forced to double up. Right? But then when I take into account the presence of ligands, okay, my first 3 electrons are obviously just going to go down here. 1, 2, 3, 1, 2, 3. But then the question becomes, where do I put 4 and then 5 and 6? Because 4 could go down here, but 4 could also go up here, right? And you see they end up filling differently. On the left-hand side here, the delta OCT, the crystal field splitting value, is small, okay? So it's easy for one of those electrons to jump up. So they fill in 1, 2, 3. All right, no problem, I can overcome that. 4, 5, because they'd rather go slightly higher in energy before they start to pair up. The 6th one doesn't have a choice. It's going to have to pair with somebody, so it goes back down here to the lower energy. On the right-hand side over here, where the crystal field splitting is large, that would come from a strong field ligand, right? Now, they can't overcome that energy barrier. They choose to pair up instead. So they fill 1, 2, 3. That's too high up. So we again 4, 5, 6. And those two different complexes that we see, right, were affected by the ligand for iron, because it was the same iron in the middle. Okay, so those have names: low spin complexes and high spin complexes. Okay. Low spin was the one on the left. Okay. Oh, sorry, the one on the right. Complexes where the electrons are paired because of the large crystal field splitting, right? It exceeds the pairing energy. So low spin complex was the one on the right. You get it because the electrons are all in the lower energy. They're paired up. Okay. That comes from strong field ligands, things on the right-hand side of the spectrochemical series. High spin complexes are where things are okay jumping up to the higher level. That results from weak field ligands. Okay? And the number of unpaired electrons, aka the number of spins, is maximized right? Because we see over here, the high spin complex had 4 unpaired electrons, where the low spin over here has 0. So that brings us to a practice problem for you to think about. Okay? Answer this question. How many unpaired electrons in that complex? Pause the video and think about it. How many unpaired electrons? You have to identify the metal, identify the charge, identify how many electrons you're dealing with, and then figure out if it's high spin or low spin. Pause the video and try that one. Okay. So what's the strategy to solve this? First thing, I need to figure out what the charge on my metal actually is so I can figure out how many electrons I'm dealing with. Because I've got that Na3, which is only a counter ion, the sodium. So that tells me my complex, right, the hexanitrocobaltate there, has to have a charge of 3 minus. So if that has a charge of 3 minus, and each of my NO2s is -1, and there's 6 of them, the cobalt itself has a charge of +3. Cobalt +3 has 6 d electrons. Okay? It's d6. You lose the 2s and one of the d's, so it ends up being d6. So that's the first thing we solve, d6. Then I look at my ligand. Is it a weak field ligand or a strong field ligand? I get that answer from the spectrochemical series, and that's a strong field ligand. That means it's got a large crystal field splitting. It's going to be a low spin complex. And with 60 electrons, they fill 1, 2, 3 in the bottom and then pair up 4, 5, 6. So at the end of the day, you end up with no unpaired electrons. So you should definitely know what these diagrams look like and how to fill them in. Okay? There's a blank diagram earlier right here. That's always the case for octahedral. You just have to know, do they fill in all the bottom first if it's low spin, or do they share the bottom and the top if it's high spin? Always the case for octahedral. Okay, so no unpaired electrons there. And those are only tricky if it's octahedral if you're D4, 5, 6, or 7. Okay, because 1, 2, 3 always go in the bottom, and then when you're 8, 9, 10, it doesn't matter where you went, okay, because they're always going to be completely filled. So that's for octahedral. We said in a previous video, tetrahedral geometries are also common. Okay? So if it's tetrahedral, we only have 4 ligands. None of the d orbitals point directly at them, but we still do see a difference in energy, okay, which is explained in this diagram. But what you should be able to take away is this is the crystal field splitting for a tetrahedral complex. Notice delta TET there, where tet is for tetrahedral. So know the 2 diagrams and when to use them, octahedral, which is more common, or tetrahedral. Okay? And then these can also be low spin, where they fill the E's first, or high spin, where they fill the T's. What's the experimental evidence for this? Well, it's similar to what we talked about in Chapter 8. Chapter 8, we talked about molecular orbital theory, which was necessary to supplement valence bond theory and explain why diatomic oxygen is paramagnetic, meaning it has unpaired electrons. We see the same thing here, right? That helps us differentiate between high spin and low spin, because complexes that end up having unpaired electrons are paramagnetic and respond to an external magnetic field. The more unpaired electrons they have, the stronger it would respond. So we finished the chapter thinking about colors of these things. And we alluded to this in the first video. Transition metal complexes, coordination compounds, are often colored. Because those d orbitals are so close together in energy, we just said they're split, either delta OCT or delta TET. Okay. But the energy difference between them is small compared to other electron transitions. So that allows photons in the visible range to be absorbed and promote an electron up, right? Most other things only do that in the ultraviolet range, but transition metal compounds can do it in the visible range. So it absorbs a photon, gets promoted up, and when that photon falls back down, right, it emits light. But just the absorbance causes things to appear colored, right? So if I change the ligands, I can change the color of the compound, because if I change it from being high spin with a small delta OCT, change the ligand, right? And now all of a sudden it's a strong field ligand, a low spin complex, right? That'll change the color of a compound. So changing the ligand, even with the same metal, can change the color, right? This explains the photons that I was just talking about. Here we see different colored compounds, right? But what's the takeaway that I want you to have here? Right? If something, here there's a whole bunch of colored complexes. What I'd like you to take away, though, hopefully you're already familiar with, right, is this idea of the color wheel. If something is appearing, let's take this one on the bottom, right? If it's appearing blue, that's because it's absorbing the opposite, right? So it's absorbing in the orange color. Things don't appear blue because they're absorbing blue, right? They're absorbing everything else but blue. And the thing that's on the opposite side of the color wheel is what they absorb the strongest. So plants appear green because they absorb red light the best. So your things that are strong field and have a large delta OCT, those are typically going to appear red and orange and yellow because they're absorbing green and blue and purple, which are higher energy because they have a larger splitting. Opposite of that, weak field ligands are going to appear in the cooler colors because they're absorbing the lower energy, warmer colors, red, orange, and yellow. So hopefully that makes sense. The big takeaway from this video is to know for sure delta OCT, delta TET, what they mean, those diagrams, how to fill them in, the spectrochemical series, right? Strong field ligands, weak field ligands, and how that splitting and where those electrons go affect both the color and the magnetic properties. And that concludes chapter 19.